questions throughout the week. So I'm going to start recording right now. And I apologize for not recording the very beginning, but hopefully your neighbors can fill you in if you're behind in the notes. Okay? But now that's recording, and I'll post this recording to our announcements page so you can go back to it if you need to. Okay, so the next section of topic 3 kind of reviews the definition of a vector. Okay, so remember from the notes that we took this past week in topic 2 that a vector is basically, let me just type this into our document. A vector is any measurement that has direction and magnitude. Okay, so those are the two things that go into vectors, direction and magnitude. Okay, now I had an email, I don't know if it was from this class or the honors class, but someone asked me, hey, what does magnitude mean exactly? Because in the video, another word for magnitude I said was size. Okay, so if you're curious about like what I mean by magnitude, if you can measure something using numbers, it's got magnitude. Okay, so height, you can measure that with numbers, it's got magnitude. Weight, you can measure that with numbers, it's got magnitude. Temperature change, you can measure that with numbers, that's got magnitude. So as long as you can measure something with numbers, it's got magnitude. Okay, now the other qualification for something to be called a vector is that it has to have direction. Okay, so last week we dealt with motion in one dimension. Okay, so I look at this little double-headed arrow I just drew. In this example, suppose you're at this starting point. In one dimension, we could associate going to the right as positive motion. We could associate going to the left as negative motion. Okay, so you can see there's directionality to this drawing I just drew. So direction can be as simple as positive or negative. Okay, now in a two-dimensional example, such as we have here with our empty set of axes again, direction is a lot more versatile. Okay, in 2 dimensions, I'm going to write this as a note on the side. In 2 dimensions, we measure direction with angles. Okay, so in 1 dimension, we measure direction with positives and negatives. In 2 dimensions, we measure directions with angles. Okay, so in the previous example, where I drew your path to school, potentially, suppose that this was our vector from the previous page. We always measure angle from the positive x-axis. Okay, so this right here, this is our direction, usually in the coordinate plane. So that's the angle theta. Theta could be anything. It could be 45 degrees, it could be 200 degrees, it could be 360 degrees, who knows? Okay, but just keep that in mind, we always measure theta from the positive x-axis. So this looks like it could be about maybe 45 degrees. Okay, so that's what direction looks like in a 2-dimensional context. 1-dimensional is up above in that little drawing. Okay, that's really all section 2 goes into. So like I said at the beginning, topic 3 is a very good review of topic 2. We're just going a little bit deeper into 2-dimensional concepts. Okay, any questions before we go into section 3 of the reading for this next week? Am I going too fast or is this good speed? It's not too fast. It's not too fast? This is recording, so if it is fast, just you know, do your best. You can always come back and look at this later. Okay. If there's no questions, you guys are a little quiet today. I don't know whether to be worried or super impressed. But if there's no questions, we'll keep going. I'm good. Okay. Okay, good. All right. So the next section I wanted to go over. Suppose for a second that we had a complex set of directions for, say, I wanted to go to school, and then I wanted to go to the post office, and then I wanted to go to the movie theater after school. So if you've got multiple destinations in a path, let's say, So let's say I'm representing these by these 3 dots. So if I wanted to go to these 3 separate destinations all throughout my day, and I wanted to figure out at the end of the day what my total displacement was, okay, you can take 3 separate vector quantities and you can add them together graphically, okay? So for example, let's say that this first vector was how to get to school, okay? Let's suppose that this next vector was how to get from school to the post office. Now let's suppose that this third vector is how to get to the movie theater from the post office, okay? Now this bottom illustration kind of shows the big picture of all of these, but you can take 3 separate vectors and you can add them together by linking them head to tail. So if you look at the bottom illustration, you can see each of these vectors is linked to the ones before it and the ones after it by drawing each vector from head to tail of the previous vector, okay? So that's how you do this graphically. You can simply just take those vectors, those arrows, you can line them up so that they're all linked together, and that is your distance traveled, let's say in this example, okay? Now remember, displacement is the as the crow flies result, okay? So at the end of my day, my total displacement is just drawn from where I started to where I ended up. I'm going to do that using this green arrow right here. Okay? So if you look at the bottom illustration, I've just drawn a green arrow representing my total displacement. Okay? So displacement is from start to finish. All right? And just to review, we could split that up, that total displacement, we could split that up into X and Y components, okay, which I'll draw here. So this would be my X component, this blue line I just drew. This is my X. And let's do my Y component in orange. Okay, this would be my Y component right here. Kind of tough to see, but you can see that little orange line I just drew. That's my Y component. Okay. Okay, so that's basically adding vectors. You do it from head to tail. Your straight as the crow flies line that you draw is your total displacement from start to finish. Okay, now just like we can add vectors, we can also subtract vectors. Okay, so if you wanted to subtract vectors from each other, it's kind of hard to envision taking these arrows and subtracting them when you're adding them, you're just putting them head to tail. I mean, how do you do that when you're subtracting them? Okay, well, the answer to that is if you ever want to subtract vectors, all you got to do is just take whatever vector you want to subtract and make it going the opposite way. So this right here, okay, is my negative version of vector B. Okay, so I'm gonna type this for you. To add, let's put it this way. To subtract vectors, simply add the negative version of the positive vector. Okay. Now that kind of sounds weird, but I'm going to illustrate with an example. Suppose for a second that I was taking vector A in the previous example. So I'm going to circle vector A right here. Suppose that I wanted to take vector A and I wanted to subtract vector B from that. Well, currently in the picture above, vector B is being added. So this is a positive vector B up here. But if I wanted to subtract it, all I would need to do is just flip its direction and draw the arrow about the same size. So I'm going to go out to there. So that blue arrow I just drew, this is the negative B version of that. So this is a negative vector B. So that's how we subtract. We simply add the negative of the vector we're interested in. Okay? So once again, to subtract vectors, simply add the negative version of the positive vector. Sounds confusing, right? How are y'all doing with this concept? Give me like a thumbs up high above your head if you're feeling good. Okay, good. All right. Going on. Just to let you know, the meeting software that we use, it kicks us out after 45 minutes just automatically. So if we get booted off, just log into the meeting again, and we'll have a fresh 45 minutes for us to play around with. Okay. So that's going to happen in probably about 5 minutes that we're going to get kicked off from each other. Okay, so maybe I can get this next bullet point in before then. Okay, so if you ever want to take a vector and multiply it by a scalar quantity, okay, scalar just means a constant. Okay, so this just means constant. So suppose for a second that I'm traveling to school. If I move to a new school that's 3 times as far away from my house as my original school was, I would simply multiply all of my vectors by that scalar quantity of 3. Okay, so let me type this out. So for example, multiplying each vector by 3 would give you triple the distance from home to school. Okay, so this 3 right here, that's a scalar quantity. It's a constant. So anytime you're multiplying vectors, all you got to do is just multiply all vectors and components involved by 3. Pretty simple. So suppose that my distance to school was 5 miles. If I multiplied that distance by 3, my resultant vector would be like 15 miles. That's pretty much all there is to this bullet point. So it's pretty easy. Okay, you're not really going to be doing that much in this section. It's mostly just geometry, Pythagorean theorem, a little bit of trig. Okay. All right. Let's keep going. Okay, this last bullet point for this section, it's really just me kind of beating a dead horse. I already talked to you about resolving components. Resolving components is just like going backwards. If you have a vector, let's say here's your vector. If you want to resolve components, your x and your y components that is, all you got to do is just figure out, hey, what's my horizontal distance that I'm traveling? That's my x component. And then figure out, hey, what's my vertical distance that I'm traveling? That's my y component. Okay, so you can do that by hand by just taking a ruler to your paper and just measuring, hey, what's the horizontal distance that I traveled? What's the vertical distance that I traveled? What I just did, that's what resolving components means. It means basically breaking a vector down into its horizontal and vertical pieces. All right? Okay. Let's keep going. All right, so here's where it gets a little more intense. So if you took geometry, I hope your geometry experience was a good one in your math class, because we're going to be doing a little bit of trigonometry in this class. So we already reviewed Pythagorean theorem. Did you all cover SOHCAHTOA in geometry? Give me a raise of hands if you did. Okay. Okay, I see some hands. Great. So review SOHCAHTOA when you get the chance. Okay. SOHCAHTOA, basically for those who are maybe a little bit rusty, is an acronym for side ratios and right triangles. Okay. So we're going to be practicing that a little bit today with some examples. So this is a very rich page I need you to take notes on really well. And I know we're being kind of brief in my agenda, but you got to know your SOHCAHTOA. So review that. Remember that you can always use Pythagorean theorem to figure out a hypotenuse if you ever want to calculate a resultant vector. Resultant vector is just a catchphrase for, hey, what's my total as the crow flies distance? Okay, you can do that by doing a squared plus b squared equals c squared. That's your hypotenuse. Okay, this is going to be a little weird. So right here, this next bullet point, this is a formula I need you to write down. This formula right here is going to allow you to find theta. Remember, we said maybe about 20 minutes ago that theta is the angle that your total displacement makes with your positive x-axis. So write that down. The inverse tangent of a sub y over a sub x will give you theta. Okay? Now, just to give you some clarity here, a sub y is your y component. Okay? A sub x is your x component. Which were just those little legs of the triangles that we've been playing around with. Okay, so make sure you've got a calculator nearby. We're going to do an example in a moment, but you got to be comfortable with trig and your calculator and with inverse trig, as you can see from this formula. Okay. And then this last bullet point, whenever you're adding multiple vectors simultaneously, remember we showed you how to do that above, you just simply set them up head to tail. Well, if you got all the components of each of those vectors, you could simply just plug them all into Pythagorean theorem and solve for your resultant vector. I'm going to show you that in this next example. So this example we're going to do in a moment is going to be very important for you to copy down and really study and get used to it. Okay, because this is a classic example of the math that I want you to be able to do in these in this topic 3. Okay. I'm kind of trying to stall a little bit because I know we're going to get booted off in a minute or two, okay? And I don't want to really start this until we get to that fresh Zoom session. So here's what we're going to do. Mr. Schmitz, are you still there?
Yes.
So I'm going to log off the Zoom session. I'm going to start a fresh one, just so we can get our fresh 45 minutes in, okay?
And will it be a different link?
It'll be the same link.
Okay, perfect.
All right, see you in a second, okay?